Okay, so this is lesson 9.2 on intermediate forms and L'Hopital's rule. So L'Hopital is a mathematician with the last name Hospital, but it's French, so it's L'Hopital's rule. And he discovered that instead of what we did early, we're going full circles now, all the way back to the first few chapters of the year when we're taking limits. So limits is always playing a role in calculus, right? Even when we're taking the integration, we're basically saying we're taking infinitely many rectangles. The limits approaching infinity. So in this case, we're just trying to go back to the original ideas of just taking simple limits earlier in the year. So when we did that, we have three ways of approaching it. First, number one was plug it in. You get an answer, you're done. Number two, you plug it in, you get terrible answer like 0/0, right? And so then you then have to use algebra to sort of clean it up, factoring, simplifying your fractions, using conjugates. And if that still fails, then you have to use graphing to go ahead and figure that out. So L'Hopital says, there's actually another way to do it. If you are finding limits, you just plug things in. When you plug it in and you get these things called intermediate form, which is 0/0 or infinity over infinity, and actually there's four other ones, but we don't really care about these in AB. BC, we care more about the other forms. So right now we really only focus our energy on 0/0 and infinity over infinity. And these are called intermediate forms because they're very weird. 0/0 is really nothing over nothing, but by definition, x over x is 1. So 0/0, if we go by definition, really should be 1, but how can it be when there's nothing over nothing, right? Same thing with infinity. You don't know about which infinity is over what infinity, so maybe one infinity is bigger than the other. Again, there's just a lot of arguments there. So in any case, those are our intermediate forms. And L'Hopital says, wait, when you plug it in, you get these things. Fear not, you don't have to do any more algebra. You actually have derivatives now to help you. You simply then show me that you have intermediate form. Then you take the derivative and then you plug it into the derivative. You plug the limit into the derivative. If you still get intermediate form, you keep taking the derivative, plug it in until you don't get intermediate form, right? Until you get an answer. So in some ways, this is actually quite nice. So let's go ahead and see, all right? But key point is you have to plug it in first. You have to establish that you have intermediate form. So we're just plugging it in. It's a lot of algebra. Okay, first thing says, number one, find the limit if it exists. We're finding the limit as x approaches 1 of this function. So first thing you want to do is plug in the 1. So 1 cubed minus 3 times 1 plus 2 all over 1 squared minus 2 times 1 plus 1. That gives me 1 minus 3 plus 2 over 1 minus 2 plus 1. Yes, it gives me intermediate form. Beautiful. That means then I can now do L'Hopital's rule. L'Hopital's rule says, okay, now that you have established that, you're still taking the same limit, but instead you take the derivative of the top, which is 3x squared minus 3, and you take the derivative of the bottom, 2x minus 2, right? And you plug it in. You plug it into this new function, and you get 3 times 1 squared minus 3 over 2 times 1 minus 2, which gives me 3 minus 3, 2 minus 2. I still get intermediate form. Again, no worries. L'Hopital says, do it again. Take the derivative once more. So limit as x approaches 1. The derivative top becomes 6x. The bottom derivative becomes 2. You plug in the 1, you get 6 times 1 over 2. My limit is equal to 3. And that's it. That's your limit, right? So again, the key point is just take derivative, plug it in, and keep going until you get a good answer, or at least get an answer that is not 0/0 or infinity over infinity. Be careful. I always get students asking this. Is 0/1 indeterminate? No, 0/1 is 0. 0 over anything is 0. Vice versa. Something over 0, what does that mean? Something over 0 means you're dividing by a really small number, so your answer is actually infinity. So those are not indeterminate form. Indeterminate form is only when top and bottom are both zeros. If one of them is 0, it's actually doable, okay? All right, so let's go ahead and look at this one again. Number 2, we're finding a limit as x approaches 0. So first thing we want to do is plug it in. You get 0 plus 1 minus e to the 0 over 0 squared. That gives me 0 plus 1 minus 1 over 0, which is 0/0. So yes, we do have indeterminate form. Okay, now we got to take the derivative. Go ahead and now use L'Hopital's rule. The derivative top is 1 for the x. This is 0. minus e to the x is minus e to the x. The bottom becomes 2x. Okay, now we're going to plug in 0 again. 1 minus e to the 0 over 2 times 0. That's 1 minus 1 over 2. Oh, sorry, over 0, not over 2. Over 0. So that gives me 0 over 0. Indeterminate once more. So we're going to take the derivative one more time. Limit as x approaches 0. 1 is gone, so just negative e to the x over 2. Plug in the 0, you get negative e to the 0 over 2, negative 1/2. And that is your limit. In our cases, most of the time, at most, we get 2 indeterminate forms. Sometimes it gets crazy, gets you 3, but a lot of times 2 or 3 steps is pretty much as far as we go. It's not going to be like 7 steps, okay? All right, same thing, number 3, let's go ahead and plug in our numbers. We're trying to practice our e values and our trig values, so make sure you remind yourself of those. Plug in the 0, you get e to the 0, minus e to the negative 0, minus 2 sine of 0 over 0 times sine of 0. Okay, that gives me 1 minus 1 minus 0 over 0, 0 over 0. Awesome, indeterminate form. Go ahead and now take the derivative. Limit as x approaches 0, e to the x minus e to negative x, bring down the negative from the negative x, e to negative x. Don't forget chain rule, right? Minus 2 cosine of 0 over, okay, be careful. The bottom here is product rule because you have x times sine x. You got to take care of product rule there. So the derivative first is the derivative of x is 1. So 1 times sine x plus x, that's keeping this derivative, keeping that original function, and then times the derivative of sine x, that's cosine x. Okay, so yes, if the function themselves on the top or bottom are products, you still need to apply your product rules. Okay, now go ahead and plug in your 0. You get e to the 0 plus e to negative 0 minus 2 cosine of 0. Ooh, accidentally put a 0 there, cosine of x, all over sine of 0 plus 0 cosine of 0. That gives me 1 plus 1 minus 2 times 1 over 0 plus 0 times 1. So that gives me 1 minus 2 minus 2 over 0, 0 over 0 again. Okay, all right. You can probably tell because this is notes, I'm trying to get you to do a lot more iterations of this. So limit as x approaches 0 of this function up here. So e to the x minus e to negative x, because the negative comes from that negative x up there, minus 2 sine x, but it's going to negative because the derivative of cosine x is a negative sine x. So it becomes plus 2 sine x. Oops. And then all over, derivative of sine x is cosine x. And then this piece itself is another product rule. So plus 1 times cosine x. And then you have x. The derivative of cosine x is negative sine x. Okay. All right. We're going to plug it in. We get e to the 0 minus, oops, not up there, minus e to negative 0 plus 2 sine of 0 cosine of 0 plus cosine of 0 minus 0 sine of 0. Okay, that gives me 1 minus 1 plus 0. And I get 1 plus 1 minus 0. So that will give me 1 minus 1 plus 0 is 0. All over 1 plus 1, 2. So I get a limit of 0. Okay, so that still works, even though it's a limit of 0. Okay, all right. What about plugging infinity? What does that do? Well, same thing. We'll do the same thing. So if we plug in infinity, we get e to the 3 times infinity over natural log of infinity. Well, e to 3 times infinity, so infinity, natural log of infinity. If you remember, natural log graph looks like this. As it goes off to infinity, it still goes up to infinity, so it's infinity. E to infinity is faster, but it's still infinity. So this is infinity over infinity, hence indeterminate form. Okay. All right, then we can go ahead and plug in, apply our L'Hopital's rule. Limit as x approaches infinity. The derivative of e to 3x is e to 3x times 3. The derivative natural log of x is 1 over x. So clean that up because I don't want to keep it as that. So that becomes multiplied by a reciprocal. Instead of dividing by 1 over x, you're multiplying by a reciprocal, so multiplying by x. So you get 3x e to the 3x. Plug in infinity, 3 times infinity, e to 3 times infinity, 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 infinity. My answer is infinity. Okay, all right. Last one here. What if it's one-sided? It actually still works, even if it's one-sided. Remember this plus and minus from a long time ago? It still works. So it still works the same way. We're gonna assume it's just approaching 2 from both sides. All right, so go ahead and plug it in a 2. You get natural log of 2 minus 1 over 2 minus 2 squared. So natural log of 1 over 0 squared, natural log of 1 is 0, 0 over 0, indeterminate form. Okay, now go ahead and take the derivative. I get limit as x approaches 2 from the positive side. Natural log of x minus 1 is 1 over x minus 1. The derivative of x minus 1 is 1, so I don't have to worry about that. The derivative at the bottom is chain rule 2, x minus 2 to the 1 power, and then x minus 2 has derivative 1, so again, I don't have to worry about that. So I'm going to clean this up before I plug it in because this is just not very pretty. So you have 1 over x divided by 2 times x minus 2. All those are all going to go to the denominator. So you have 2, x minus 1, x minus 2, like so. Plug in your 2, you get 1 over 2 times 2 minus 1, 2 minus 2. You get 1 over 2 times 1 times 0, 1 over 0. This is not in determinant form. We talked about this. If you're really divided by 0, you're not really divided by 0. You're dividing by a really small number. 1 over a really small number, reciprocal that becomes a really big number. So this limit is infinity. Okay? All right, so again, I think we've come full circle from doing antiderivatives. Now we're back to limits and taking derivative at the very end of our curriculum. So that's it, the last lesson.